Thank you everyone for attending today. So yeah, I would like to start the talk asking how many of you have fine-tuned an LLM here? Well, a few. And have you fine-tuned on good data? Do you think it was good data? Yeah, that's something that we sometimes forgot. So yeah, I'm Gabriel. I'm a machine learning engineer working at Argila. And yeah, if you don't know Argila, we are a small company building a data AI platform for building data set and gathering annotations. And we are building this platform for kind of two roles: the machine learning engineer who sets up the data set, and then the domain experts that that annotate this data. And yeah, you can use this platform, of course, for building data set for LLMs. And yeah, if you don't know, LLMs are large models that can work with natural languages like English, Spanish, or even Lithuanian, as we have seen in some other talks. And yeah, you usually need a few GPUs to train those. So what are we doing as a small GPU poor company to fine-tune a large language model when we decided to become data rich? And why data rich? Well, it is quite easy. These models are trained on data. So if you have better data, you basically get a better model. It is an easy equation. So, and yeah, also thanks to the community and the researchers, right now there are new techniques for training, like LoRa, that makes fine-tuning an LLM not hard if you don't have enough GPUs. You can even do that with a consumer GPU or a free Google Colab environment. So the only thing that is missing, or that you still have to do, is to is to improve the data. And once you have this, once you have data of high quality, you can fine-tune an LLM with a consumer GPU or a Google Colab environment. So yeah, today I will be explaining some experiments that we did in Argila to improve some open source dataset, and also what we did to create new dataset. Before jumping on these experiments, I will first start explaining the different phases that an LLM, the different training phases that an LLM is trained on, because it's important to understand those and what kind of data do we need for each. So the first phase is the pre-training phase, in which we initialize a random architecture with random weights. And basically, we want to gather as much data as possible because we want the LLM to learn how language works and to gain general knowledge. So usually the quantity is prioritized over the quality on this phase. And how do we achieve the LLM to learn something? Well, we use this technique, mask language modeling, in which we take a sentence, we randomly mask some words or tokens, and the objective of the LLM is to predict the mask token, the original word. And with this, the LLM will learn how language works and gain knowledge. These kind of LLMs, usually, as they are big models, can also perform some tasks. But usually we have a second phase that it is called instruction tuning or supervised fine-tune, in which what we want to do is the LLM to learn a specific task. And we usually have a data set, which is a instruction and a desired response, and usually is created by humans, but this is not completely true, as we will see later. And usually we have this kind of data sets in which we have a instruction from the user, how many helicopters can a human eat in one sitting, and then a desired response from the LLM. Humans cannot eat helicopters. And also in the case of LLMs, as they can be used for chat, we also have this other kind of data set in which we have a chat, several iterations, let's say. Okay, so yeah, we have fine-tuned an LLM for doing a specific task, but there is something still that we need to do, that it is to align it, to do preference tuning, because maybe we want the LLM to do this task, but following certain aspects. And for this kind of tuning, we need a preference dataset. And a preference dataset is basically an instruction, like the one we have seen before. And then, yeah, we ask to the supervised fine-tuning LLM from the previous phase to generate several completions for that instruction. So we have several completions, and then we have a human telling which one they prefer. In this case, it's the same assistant as before, but we want it to respond in the style of a pirate. So yeah, we prefer the one from the left, which is argh, scallywag. That is not possible. Yeah. And how is this preference tuning done? Well, it is using algorithms like reinforcement learning from human feedback, which also requires a reward model, which also requires more GPUs. And yeah, luckily for us, we have something similar that it is called direct preference optimization with this beautiful loss function that is trying to maximize the likelihood of the choosing response and minimize the likelihood of the rejected response. And okay, if you don't like if it is hard for you to create a preference dataset for DPO or reinforcement learning with human feedback, there is an alternative, KTO, in which you basically have the human interacting with the supervised fine-tuning LLM. And yeah, the only thing that the human has to do is to give thumbs up or thumbs down to the given response. And with that, we can do this phase 2. Okay. If you want, we have a series of blog posts that we developed with Mantis NLP, a collaboration. So yeah, you have more information about alignment methods there. So why is data quality relevant now? Well, first, as I mentioned, retraining an LLM is expensive process. You usually need thousands of GPUs. And not only that, there is also a scarcity in the market, so it is not easy to get access to these GPUs. Then, luckily for us, some companies have decided to follow the holy path of open source. So we have open source models of all the size from 7 billion to 70 billion parameters that we can take and fine-tune for our specific task. The only thing that we have or that we need is the right data. Also, there is several libraries that we can use to do this fine-tune and many alternatives to reinforcement learning with human feedback like DPO or KTO. And lastly, there has been a trend for synthetic data, and this is to use LLMs to generate data to train LLMs, as crazy as it sounds, and then also using LLMs to also annotate this data. And the community has put a lot of effort in this, in developing these methods, but also has forgot a bit about how important is human evaluation. Okay, so yeah, given this this introduction, today I will like to talk about these 3 experiments that we did, starting from what we did to improve Stanford Alpaca dataset, what we did to improve ultra feedback dataset, and one collaboration that we did with Hugging Face to basically create a prompt dataset from humans. So yeah, I will start with the Stanford Alpaca, which is a synthetically generated dataset created by Stanford. And they used TestDaVinci 3 from OpenAI, which I think it is no longer available, and the prompt method self-strat, which basically, starting from a seed set of data of instruction and response, you can generate more synthetic, more data similar to that and to other topic. And yeah, this is the distribution of the verbs, the most used verbs that appear in the instructions, and the outer cycle is the nouns that were followed by this verb. So for example, in this data set, we could find, explain the concept of gravitational attraction and instructions like that. So yeah, awesome. We had a data set with 52,000 rows, but it had some problems or limitations. The dataset contained reference to documents, maybe fictional, maybe not, but yeah, this is not desired, and it hallucinated, which is, the fine-tuned model hallucinated when using this dataset, generating fake stock price, and apart from that, it also suffered for generating stereotypical data, and it was toxic. So what we did in Argila is to basically train a test classifier to detect this bad instruction response pair, and for that we annotated 1,000 manually, and we trained this test classifier with setfit, which is an awesome library. And then we loaded the records and the prediction given by this model to Argila, and using the filters, we can filter very quick the records that we are interested to check, which are the bad ones, the garbage ones. And we can also go a step further and use the score or the confidence given by this model to have humans reviewing those in which the model was not very confident. Okay, so the next dataset that we work with was ultrafeedback, which was created by OpenBNB, and it was a famous one. It was used by Hugging Face H4 team to fine-tune Zephyr. I don't know if you know it, but it was a quite good model, and it was famous. And also some other companies like LNAI trained Tulu family of models on this dataset. And it was awesome. What they did is to gather prompts from other dataset and then send these prompts to different open source LLMs to get responses and build a preference dataset. And to annotate this preference data, what they used was GPT-4. So, and how they use GPT-4? They basically send this prompt, hey, this is the instruction, this is the response that was given by the model, give me a score and a rationale behind the score. And this was the first kind of prompt that they used. Then they also used the other one on the right, in which all the responses given by the LLMs for the same instruction were sent in the same prompt and were rated by GPT-4 on several aspects, also giving a rationale. And what was the issue with this dataset? Well, first of all, it had prompts coming from Truthful QA benchmark, which is an academic benchmark used to score LLMs. So fine-tune LLMs on this dataset, the results of running this benchmark were no longer valid because we have basically trained on the test set. And then it has a coding error, which was like the biggest flaw of this dataset, in which, as you can see in the image, there were prompts which the chosen response was very bad. But if you see there on the right, we had a score of 10. So this response was very good, but it wasn't. And this was because there was a bug in the pipeline. So what we did is to basically build a new score for each of the completions and build a new preference dataset using the scores on the right, averaging the score that was given for each aspect. And this fixed the issue. And yeah, we also removed the leak rows from other benchmarks. And we went a little further with this experiment, and we trained Node 7 billion, which is an LLM that basically follows the recipe of Zephyr 7 billion beta by Hugging Face. And what we did is to fine-tune, do the fine-tune alignment using the fixed version of our dataset of ultra feedback. And yeah, finally, I want to talk about one initiative that we started with Hugging Face, which is the Data is Better Together. And what we want to do is to build impactful datasets with the help of the open source AI community. And the first thing that we did is to set up an environment to annotate 52,000 prompts. And the problem is that, as I mentioned before, in the last months, there has been a lot of effort on developing synthetic methods to generate data, but not so much human efforts. So what we wanted is to annotate these prompts using humans to give it that rate. And what we achieved is that in the first 2 weeks, we managed to annotate 10,000 prompts with the help of 320 collaborators, and then for a small subset of these prompts that were highly rated, we generated responses with Mistral Large, and yeah, we managed to train another model using Spin, which is another fine-tuning technique, and we were the first one to replicate the results from this paper. So yeah, we insist a lot on social media that data quality and human feedback are key. But if you don't believe us, then you can read these papers, recent papers that have verified that data quality is key and not that much data quantity for supervised fine-tuning and the alignment phase. The first one is Lima, less is more for alignment, with a data set of 1,000 rows of high quality that they manually gather from other sources and manually develop and improve. They managed to train Lima 65 billion model, which in comparison to GPT-4, the responses were 43% of the time better or equal, and this just with 1,000 super rows. Then we have this other paper, Data, and what they did is to build a pipeline to filter rows and to get the ones that were more complex in its prompt, that the responses were of better quality, and also that the instructions and response added more diversity to the final dataset. And what they achieve is that with 33 less times of data for the supervised fine-tuning and with 6 times less data for the alignment phase, they managed to get the same scores as Zephyr 7 billion beta, which is the model that I mentioned before. And yeah, finally, 01.ai published their report about the G family of models, which are state-of-the-art models. And they mentioned something very interesting, and is that for the instruction fine-tuning phase, they use less than 10,000 rows for fine-tuning these LLMs. And they achieve that with human annotation. And yeah, I take basically this paragraph from their paper because yeah, it's beautiful. And yeah, so data quality and human feedback are important. So how do I get started? One question that we usually receive is how many rows do I need for doing the supervised fine-tuning or the alignment phase? Well, we have from our experiments we have usually used around 6,000 and 10,000 rows for supervised fine-tuning and around 3,000 and 10,000 for DPO. And then to improve your data, start from the bottom to the top. don't go directly to the hard stuff or more complex stuff. Manually browsing or visually exploring your data can get you many insights and help you to detect patterns. And then if that's not enough, you can use embeddings to get similar records, to filter records, to add diversity. You can use test classifiers, as we have seen before, or you can even use simpler heuristic like test descriptive. And finally, using LLMs for generating data and annotating. It is fast and it is a good option, but don't rely 100% on this method. They have to be used to accelerate the human annotation process. And this is a song that was generated by AI, and it is very good. So I will share it later on Discord. And to finish the presentation, I want also to talk about a few other projects. We created this framework, this T-label, which allows you to generate synthetic data using LLMs. And next week we are releasing a new major version that will allow to build more complex, flexible pipelines, like data. Then for the data is better together, we have two other projects. The first one is to use humans for annotating a data set that will be used to fine-tune a model using KTO. And finally, we have this very interesting project that it is called the Multilingual Prompt Evaluation Project, in which we want to translate 500 prompts to other languages and then use these translated prompts to evaluate LLMs using Alpaca Eval benchmark. And I think that for Lithuanian, we haven't started yet, but so if you want, we offer you all the resources, all the code that you need to set up the annotation UI. And that was my talk. So thank you so much. And if you want, you can follow me on GitHub, and you can follow also Argila. And if you want, you can connect with me in LinkedIn or follow me in Twitter or X. I usually tweet about LLM fine-tuning and generating synthetic data. So thank you so much.
Thank you so much. Great. We do have a question from the Discord. Isaac was mentioning a few questions. So how do you choose how much to rely on LLM as judges?
That's a very good question. First of all, you want to, there are some LLMs that you can usually rely more than others. For example, in some studies that we have done, we have seen that, for example, GPT-4, the annotation given by GPT-4 usually correlates a lot with the ones given by humans. So I will say that you want to find to manually annotate first some with humans, and then some others with the LLM, and do this study to see how it correlates. And based on that, you can set a threshold on how much you should rely on the LLM.
Okay, thank you so much. Any other questions from the audience? Yep, it is.
What do you think about model merging, like both LLMs?
Model merging is a very interesting technique. Basically, what you do is you take weights from different LLMs and you build a new LLM, merging the weights of the different LLMs. And it is weird, but the generated LLMs are better. And it is kind of a mystery on how they work, but they achieve better scores. So there is an interesting technique, and there has been recently work about this too from Sakana AI, which is a lab from Japan, and they published a very good paper about model merging, and they use this to improve models for Japanese.
Interesting. Okay, thank you. Any other questions? Okay, so warm applause to Gabriel for the great presentation. Next up in